So I'm Michael Munroe, and I work for Elma Electronic. We do systems, system packaging, backplanes, components, all aimed at the embedded computer industry. And we've been supporting the Eurocard architecture since the very early 80s. And my specialty is working on the backplane architectures, and that's been exciting. You know, VPX next year will really be 10 years old. It's hard to believe. We started working on VPX backplanes in 2006 when we were still filling out the VXS product line. And there have been so many developments, so much paper, so many trees killed, that it's, you know, sometimes people think how can you need more and more? But we all know that the capability of VPX is getting greater and greater. So this is, I was going to show a slide, cartoon about, how we always want to do another standard to take care of everybody's use case, and we just really end up with just one more use case. This is the converged backplane that's being developed by CERDEC and together with ONR, and I understand the Air Force is now getting involved. And it is really an example of it incorporates some of the most recent developments in VPX over the last several years. And I think that it is also sort of a platform to show the wide range of capabilities and slot types that are available to engineers going forward. So we've gone over a lot of these features, but in a lot of architectures, we've wanted blind mate coaxial connections through the backplane, and we've accomplished them different ways. There really hasn't been a standard way that I'm aware of. We've had the P0 in VME, we've had the Zone 3 in ATCA, but having a standard solution allows a lot more integration and leaves the front panel free for other uses. The same thing with fiber optics through the backplane. I remember back in the early 90s, we had a company I was working for had a P0 connector that offered fiber optic through the backplane, but it really never took off at all. I think one of the most important developments, and one that's probably occupied more emails and more discussion in meetings, has been the introduction of radial clocks and clock termination. With the just clock termination alone is a subject that's been changing as we've been moving to faster and faster PCIe, and so we need now local clocks, between cards that share an expansion plane. But having multiple radial clocks allows us to do things within VPX that previously could only be done in PXI or PXI Express or VXI, going to VXI 4.0. Even ATCA and micro TCA really had a way to do some radial clocks, but we've got the option of at least 3 radial clocks now. But a way to integrate both, thanks to a lot of hard work on the committee's part, we have the ability to have both bus clocks or radial clocks. So we've really worked hard to keep backward compatibility. And of course, the data rates are going faster and faster. I don't need to talk about that. But now we have the possibilities of an RF switch because we have a wide variety of coaxial connectors and RF slots, and I'll show you a little bit more about that as well. And the same thing with optical I/O. There's developments there that really are going to allow that to expand tremendously. So a lot of architectures, we've had to move from one standard to another to go faster and faster. Along with that, it's gotten more and more time-consuming to do the engineering. As we move from 10 gigabit channels to 16 gigabit channels, we now have to take into consideration the specific design and launch on the daughter card when we want to simulate the entire system. So we have to look at the daughter card, the switch. And that's only likely to increase even when there's a new connector plan, or Tyco continues to improve the connectors. We know about the RT2R. They're working hard to make it easier to support PCIe Gen 4 on the multi-gig, and I'm sure other people will work on this as well, but there's some clear paths to do that. But even as we get faster and faster connectors, it takes more and more time. It's going to take more and more time to implement them in different types of custom applications, even with if we complete VITA 68.1 and .2, or .0 and .1 and 2 as well. Moving to fiber optics will allow us right now to have some, an expansion plane between two cards that can transmit, so much information across them. It's hard to really imagine how it'll be utilized, but I have no doubt that we will. Everyone has predicted that you had enough computing or enough I/O has always been proven wrong fairly quickly. But just think, well, I'll go into that a little bit more. So this shows most of the unique slot profiles that are used in the converged backplane that I just had in front of you. So I have in light gray the ones that are really unchanged that you'll find in the existing R2 version of VITA 65. And the dark ones are ones that we've actually started using, or at least ones very close to it, but those represent the ones that I really want to talk about in just a little more detail. We've talked about fiber optics. Those of you who've heard me, I've been on this particular jog, not as long as Ray Alderman, but for a pretty long time. This is a backplane that we offer, and this is the half-size module. This is VITA 66.4 that was developed specifically for 3U VPX, though it can be used in 6U. You can actually use the full width one that's the 66.1 on 3U as well. One nice thing about this half-size one, it has the same footprint as a standard RF module that will have 4 cavities. The only thing that VITA did in developing this, and by the way, we had a collaboration from a group to get the vendors to start working on this early on, and I told them to put it the other way because I didn't know what the heck I was doing, and it turned out we could arrange it this way, which allows the ribbon on the daughter card to lay flat against the daughter card. So this part right here, the optical ferrule in the middle, that's an industry standard dimension. So there's a lot of product out there today that you can put into that ferrule. There's several levels of alignment. This has 3 alignment pins for the housing, and then there's this major alignment. It floats in there, and then you see the 2 holes that are actually visible. There's pins on one side that fit in, so that's sort of the final alignment. You can't see in this picture, but can be 12, 1 row of 12 or 2 rows of 12 fibers between there. So today, it's very common to have 10 gigabit channels, 28 gigabit channels. There's probably more than a half a dozen vendors who offer devices that will drive that fast. So you can imagine that with 2 rows, if you had 12 fibers, you really would have 240 gigabits of data bidirectional just in that alone. One thing that we haven't really talked about, but with this type of parallel optics, we talked yesterday. A presenter was talking about the difficulty in having the movement of the fiber. That's, of course, fiber is very fragile. These, though, the fibers are glued directly, not just the cladding, but they're glued into this, and they have to be pressed, and they're polished in such a way that the actual ends come in tight contact with each other. And so, as you might expect, 24 fibers, 2 rows, takes twice as much force as 1 row. They really have to be pushed together with a lot of force, so if there's any debris and it's a plastic fiber, it's not just a matter of clearing out the debris, but it's the expensive process of re-terminating it. And also in 3U, for instance, we generally have 1 injector. If it's a 48.1 kind of application, with front panels, you have 1 injector typically because front panel space is too valuable to have 2 card injectors, and that means we're just pressing in on one edge of the board. So as we have to put more and more force, and we're only loading one end of the board, it's a mechanical nightmare. This is just, I don't know if this is good enough. I try and take these pictures, but if you can see, there's 12 small holes in there. This shows just the back of that backplane you saw before. There's 1 fiber going into this position and into the 3rd position. There's 2 fibers coming out. So that's kind of demonstrating 24 fibers in 1. So, and here's Pentec has been one of the first company, possibly I think the first company to implement the optical drivers produced by Samtec, the Firefly product, and this shows the half-size VITA 66.4 module sitting there, so those signals can be passed directly through the backplane, can be passed to another card in another slot. It could, in another type of application, be bringing data in from a sensor field. Here's yet another device. This has pigtails. This has the advantage of, well, it can be an advantage of having the MT ferrule integrated directly into it, so you can use more standardized harnesses, and it will be easier to change it if you need to. So this is something that I've been talking about a little bit. It's turned out it's fairly hard to implement, but and so I think it was introduced 2 years ago at OFC. It is a standard MT ferrule, same size as what we're dealing with. It looks a little different because it's clear, and it supports, instead of rows of 12, rows of 16. Now, what really makes this quite practical for us and actually gives some advantages is that these are all lens. So these are what people call expanded beam, columnated lenses. So they have them on both halves. This means now that you no longer have to have that forcing together of the actual ends of the fibers, but now when it closes, the fibers are actually still back, the tips of the fiber are back a couple thousandths. So this means there's 3 different kind of things that derive from this. 1, it takes less force. Now you only have to hold them together enough to keep them from chattering. It's just you don't want them to move apart, but you don't have to push them so hard that you're deforming the fibers. The second thing is that there is much less mechanical stress on the whole assembly, particularly the ferrule, so that we can actually do 6 rows of 16, because we can go closer to the edge because we don't have to depend upon the mechanical strength of the block of ferrule material. And then, of course, the other thing is that if you do close on debris, you certainly have to clear the debris out because it will block it in the same way. But there's a very good chance that it hasn't been pushed together so hard that you've actually damaged the interface. And I think that's a very important feature as well. But there's drawbacks. Right now, they're having a hard time getting enough vendors qualified to assemble it. Tyco's been working on this as well as a number of other people who are in the telecom community. For our community, this isn't so interesting right now for deployed applications because this material that molds the outer part of the ferrule is also what the lenses are molded. The lenses are integral. And while that's an efficient method, there's a compromise between the choice of materials. So a wide temperature range product is not yet available. But with 64 fibers in one half-size module, you now have the possibility of breaking it out into 8 fat pipes that could go elsewhere. And so each of those terminals, the far ends, could have 8 fibers, 4 transmit, 4 receive. And the end ones that might just go to another slot or could go to a cable to the outside world, those don't have to be the more exotic one that passes through the backplane. And I've got a sample of that if people want to see it later. So this is now, so those were all things that we were able to do with this type of opening in the backplane. But I mentioned that we had a double size opening, and then we also have RF contacts as well. And there's been another development that is already being implemented in that CERDEC backplane. We had some standard full size and half size, and unfortunately, because of when the specs were done, the full size one is not compatible with full size optical module. In the backplane, this is just a cutout in the backplane with mounting holes and alignment holes, but it's just an opening in the backplane. So there were ones initially that had 8 contacts, and there was the half size that had 4. Now in the same space in the stack as you have 8, this is just an example of 10, but with much smaller coaxial contacts that can be allowed in 67.3, you really can do a lot more than what's even shown there. And the important thing with this is that when people build RF modules on a card, there are often, multiple levels of PC boards in them, and they'd really like to be able to direct launch right off of them into the backplane connector. VITA 67.3 is really a very open spec. It only defines the outer mechanical envelope. It only defines the opening in the backplane and the mounting holes. Everything else, it also lays out a nomenclature so that you can define where the contacts are, but the mounting plane of the 2 contacts is defined. So there's really, it takes care of a lot of the mechanical requirements that would really be sort of who cares, but just need to be done. But it establishes those so that with very little added information, we can implement different arrangements of contacts. If you have a backplane, whether it's a development one or a fielded one, because the opening and the mounting holes are the same, you could swap out a new card, you could swap in the new mating connector for it, and that allows some flexibility. Now, there's a lot of different uses we can use this for, whether it's antennas or distributing very high-speed timing signals. But if you wanted to distribute radial clocks coaxially, you might have a bunch of contacts on the timing card, and you might distribute some to each other slot. Now, I want to point out that this is flexible cable that is available. But for an application, if this was really a radial timing clock, this would be rigid, semi-rigid coax that would have to be laid in very carefully, and it's an engineering effort in its own. So I'd like to say we now have more, VPX comes to us with the ability to bring more power onto a slot than we really can cool by any known methods. I mean, even liquid flow through is not going to be good if you were to have 2 cards with over 500 watts, 2 3U cards with over 500 watts of power each, unless you're doing a lighting system or something. We also now have more bandwidth. Whoops. More bandwidth slot to slot. If you had 8 fat pipes, I guess, running each at 50 gigabits per lane, we could have something like 800 watts 800 gigabits per second for each of those fat pipes. If you're just going to slot, you have 1.6 terabytes. I should look there. So we haven't talked about system management. We haven't talked about the control planes that are features having these radial clocks, though. VPX is today equipped with so many features that I think it is likely to take us far into the future You know, the copper connections alone allow us a lot of flexibility. There's a lot of I/O available through them. And I think the way in which we've implemented these additional slots, it really becomes convenient to mix standard slots with existing slots. You can have slots where you don't have those modules installed, and you could install another standard connector with only minor modifications. So it's really been exciting. I have a sample. I don't want to pass it around because it's took me over a year to get, but if somebody wants to see the 160, the 64 fiber ribbon I have, and I think Dave may already have passed a backplane that has, I think, the optical modules installed. So thank you very much, and I hope you enjoy that.